We thought we mapped the cosmos. We were wrong. James Webb just shattered the boundaries of how far we can see into space and time. Galaxies are appearing where none should exist. Distances refuse to match our equations. The numbers we trusted for decades are collapsing under new evidence. If you enjoy mysteries that challenge everything we thought was real, hit that like button and subscribe. What Webb is revealing about the actual size of existence is forcing scientists to admit we barely understand the universe at all. Take a breath. We voyage to the edge of everything. The universe has a horizon, not a physical edge, a limit to what light has had time to reach us. Since the Big Bang happened 13.8 billion years ago, we can only see objects whose light has traveled that long. Everything beyond that distance remains invisible. The observable universe stretches roughly 46 billion light-years in every direction. That number surprises people. How can we see 46 billion light-years if the universe is only 13.8 billion years old? The answer is expansion. Space itself stretches. While light travels toward us, the universe grows. An object that emitted light 13 billion years ago has moved much farther away during the journey. By the time its photons reach our telescopes, that galaxy sits over 30 billion light-years distant. The expansion inflates distances faster than light closes them. Webb changed what we can observe within that horizon. Previous telescopes, including Hubble, could detect galaxies out to certain distances. Their instruments had limits. Faint objects remained hidden. Webb broke through those barriers with a mirror 21 feet across and sensors cooled to nearly absolute zero. It sees deeper into space than any instrument humans ever built. The first deep field images proved this immediately. Scientists pointed Webb at a patch of sky smaller than a grain of sand held at arm's length. They let it stare for days. Photons accumulated. When the data came back, thousands of galaxies appeared. Many had never been detected before. Some sat at distances Hubble could barely glimpse. Then came the records. Within months, Webb identified galaxies at redshifts above 13. Redshift measures how much the universe has expanded since light left an object. Higher numbers mean greater distances and earlier times. A redshift of 13 corresponds to roughly 300 million years after the Big Bang. Webb found galaxies forming when the cosmos was barely an infant. Each new observation pushes the boundary further. Astronomers discover galaxies at redshift 14, then 15. The most distant confirmed galaxy sits at a time when the universe was only 230 million years old. That breaks every prediction. Models said galaxies needed longer to assemble. The early universe should have been too chaotic for organized structures. Yet, there they are, fully formed, bright, massive, staring back through over 13 billion years of expanding space. The observable horizon has not moved. It still sits 46 billion light-years away. What changed is our ability to see objects close to that edge. Webb detects light so faint and stretched that previous instruments registered nothing but darkness. We are approaching the ultimate limit of what the universe allows us to observe. Every photon Webb captures traveled unimaginable distances through expanding space. Gravity wells bent their paths. Cosmic expansion stretched their wavelengths. They survived for over 13 billion years just to reach our mirrors. Each image is a message from the edge of time itself. But there is a problem. The farther Webb looks, the stranger things become. Scientists measure the universe's expansion in two ways. The first method uses nearby objects. Astronomers observe certain types of stars called Cepheid variables. These stars pulse at predictable rates. Brighter ones pulse slower, dimmer ones pulse faster. By measuring the pulse rate, you determine the star's true brightness. Compare that to how bright it appears from Earth, and you calculate its distance. Using Cepheids, astronomers build a cosmic distance ladder, measure nearby stars. Use those to calibrate distances to nearby galaxies. Use those galaxies to measure farther ones. Step by step, you map distances across hundreds of millions of light years. From those measurements, you derive how fast the universe expands. This gives you the Hubble constant, the rate of expansion. The second method uses the cosmic microwave background. This radiation fills the entire universe. It emerged 380,000 years after the Big Bang, when the cosmos cooled enough for light to travel freely. By analyzing tiny temperature fluctuations in this ancient light, cosmologists reconstruct the early universe's properties. From that, they predict how fast the universe should be expanding today. The two methods should agree. They do not. The Cepheid measurement says the universe expands at roughly 73 kilometers per second for every megaparsec of distance. A megaparsec is about 3.3 million light years. The cosmic microwave background measurement says 67. That 6-unit difference sounds small. It is catastrophic. One of the measurements must be wrong, or both are right, and something fundamental about the universe is missing from our models. This discrepancy is called the Hubble tension. It has persisted for years. As measurements improve, it grows worse instead of better. Webb was supposed to resolve this. Its precision observations of Cepheids in distant galaxies confirmed the higher expansion rate. The tension did not disappear, it solidified. The universe genuinely appears to expand at different rates depending on how you measure it. This implies terrifying possibilities. Maybe dark energy, the force driving expansion, is not constant. Maybe it strengthens over time. Maybe the early universe expanded differently than we thought. Maybe our understanding of cosmic evolution is fundamentally broken. If the expansion rate is wrong, distances are wrong. The size of the observable universe depends on expansion. Faster expansion means objects are farther away than we calculated. The universe is bigger. Slower expansion means smaller. The mismatch suggests we do not even know the correct size of the cosmos we inhabit. There is another option. Maybe space itself behaves differently in different regions or eras. Maybe the rules governing expansion changed. Maybe the universe is not uniform. That shatters the cosmological principle, the assumption that the universe looks the same everywhere on large scales. Scientists check their measurements obsessively. The data hold, the tension remains. Something is deeply wrong with our picture of cosmic scale. We thought we understood how big the universe is and how it grows. Webb is proving we do not. And this is just the beginning of what does not add up. Webb's first images revealed something unexpected. Galaxies in the early universe look too mature. They shine too brightly. They contain too many stars. They organized into spiral and elliptical shapes too quickly. According to models, these structures needed billions of years to develop. Webb found them fully formed less than 1 billion years after the Big Bang. Brightness indicates mass. More stars mean more light. When astronomers measure how much light a distant galaxy emits, they estimate how many stars it contains. Early galaxies should be small and faint. They represent the universe's first attempts at building structure. Gas clouds barely beginning to collapse. Stars just starting to ignite. Instead, Webb sees giants. Some early galaxies shine with the luminosity of hundreds of billions of stars. That mass should not exist yet. The universe had not had time to pull together that much matter into organized structures. Gas should still be dispersed. Gravity should still be drawing things together slowly. Size tells a similar story. Distant galaxies span tens of thousands of light years across. They show distinct arms, bulges, bars. These features develop through galactic interactions and internal dynamics. Simulations say this takes time. Galaxies merge, collisions shape them, stars orbit and redistribute. The process is gradual. Yet here are fully mature galaxies when the cosmos was 600 million years old. They did not have time to go through the expected evolution. Either they formed faster than physics allows, or our timeline is wrong. Brightness and size also affect distance estimates. If a galaxy appears brighter than expected, astronomers might think it is closer than it actually is. If it is larger, the same issue arises. Webb's findings suggest some distant objects might be even farther away than their redshift indicates. The universe could be larger than we thought, simply because we underestimated how intrinsically bright and big early galaxies could be. There is another explanation. Maybe the first stars were different. Population. 3 stars, the theoretical first generation, should have been massive and extremely bright. If early galaxies contained disproportionate numbers of these giants, their light output would be higher. The galaxies would look more luminous without needing more total mass. But that creates its own problems. Massive stars die quickly. They explode as supernovae within a few million years. If early galaxies were full of these monsters, they should have been blasting themselves apart. The supernova feedback should have expelled gas and stopped star formation. Yet the galaxies Webb sees are thriving, not self-destructing. Every explanation for why these galaxies are too bright and too big creates new contradictions. Increase the star formation rate and you violate cooling timescales. Increase the efficiency of galaxy assembly and you break gravitational models. Make the first stars more massive and you trigger feedback that should shut everything down. The data are solid. Webb's instruments are calibrated. The galaxies are genuinely brighter and larger than models predicted. Either our models are fundamentally wrong, or the early universe operated under rules we do not understand yet. What comes next makes the mystery even stranger. What we see is not all that exists. The observable universe stretches 46 billion light-years in every direction. That gives a diameter of 92 billion light-years. Sounds incomprehensibly vast. It might be nothing compared to the actual universe. Light speed limits what we observe. Photons travel at 186,000 miles per second. Nothing moves faster. Information cannot reach us from objects whose light has not had time to arrive since the Big Bang. Those regions are beyond our cosmic horizon. They exist, but they are invisible and forever will be. Cosmologists estimate the full universe could be at least 250 times larger than the observable portion. Some models suggest it is infinite. There is no edge. Space continues forever in all directions. The observable universe is just a sphere around Earth, determined by how far light can travel in 13.8 billion years while space expands. This means the universe we study represents a tiny sample. Imagine standing in the middle of an ocean and only seeing water out to the horizon. You can measure waves, temperature, salinity within your visible range, but the ocean extends far beyond. What you observe might not represent the whole. The water could be different elsewhere. Currents could flow in unexpected ways. Islands or continents could exist outside your view. The universe is the same. Everything we measure, every galaxy, Webb detects, every structure we map, exists within our limited sphere. Beyond that boundary, the cosmos continues. It might look similar, it might be radically different. We have no way to know. Expansion makes this worse. The universe is not static. It grows. As it expands, distant regions accelerate away from us. Objects beyond a certain distance, recede faster than light can travel toward us. Their photons never reach Earth. The cosmic horizon is not just a distance limit, it is a causality barrier. Events happening beyond it can never affect us. We can never affect them. This creates a disturbing realization. Most of the universe is permanently invisible, unreachable, unknowable. We are confined to a bubble 46 billion light-years wide, surrounded by vastness we can never explore or even observe. The observable universe is also shrinking in a sense. Expansion is accelerating. Dark energy drives galaxies apart faster over time. Objects currently visible will eventually cross the cosmic horizon and disappear from view. In trillions of years, distant galaxy clusters will redshift into invisibility. Future astronomers will see a lonelier cosmos, with fewer galaxies in their observable sphere. Webb pushes us to the edge of our bubble. It detects the faintest, most distant galaxies light can show us, but it cannot break the horizon. No telescope can. The universe beyond remains speculation. This raises a philosophical question. If the full universe is infinite, or even just vastly larger than the observable portion, what does that mean for our understanding? Every measurement we make, every constant we derive, every theory we test, applies only to our local region. The laws of physics might differ elsewhere. Fundamental constants could vary, structures could form differently. We claim to understand the universe. In reality, we understand a bubble. The true scale of existence dwarfs our knowledge, and what Webb is revealing about our bubble is already terrifying enough. 600 million years after creation, galaxies already looked ancient. The Big Bang happened 13.8 billion years ago. For the first few 100 million years, the universe was dark. No stars existed. Hydrogen and helium gas drifted through expanding space. Gravity slowly pulled denser regions together. Eventually, the first stars ignited. Then the first galaxies assembled. Theory predicted this process would take time. Early galaxies should be small, irregular, chaotic. They would grow through mergers. Over billions of years, they would organize into spirals, ellipticals, and other familiar shapes. By the time the universe reached a few billion years old, mature galaxies would exist. Webb found them at 600 million years. These are not proto-galaxies. They are not messy clouds of gas with a few scattered stars. They are organized structures. Some contain spiral arms. Others show central bulges. Many shine with the light of hundreds of billions of stars. They look like galaxies from the modern universe, just redshifted into extreme distances. The mass of these galaxies is staggering. Astronomers estimate some weigh as much as 100 billion times our own star's mass. Building that much structure requires pulling together vast amounts of matter. Gas must collapse, stars must form, gravity must organize everything into a coherent system. This cannot happen quickly, or so we thought. The timeline does not work. 600 million years after the Big Bang, the universe was still very young. Matter was more evenly distributed. Density fluctuations were smaller. Dark matter halos had less time to grow. The conditions for rapid galaxy formation were not ideal. Yet, these galaxies exist. They assembled in a fraction of the time models allow. Either the models are wrong, or the early universe was fundamentally different from what we assumed. One possibility is that star formation was far more efficient in the early cosmos. Gas converted into stars faster. Less material was wasted. Feedback from supernovae did not shut down star formation as effectively. Galaxies could accumulate stellar mass quickly. Another possibility is that dark matter behaved differently. Maybe dark matter halos formed earlier and grew faster. Maybe they were denser. stronger gravity would pull gas together more quickly. Galaxies could assemble in hundreds of millions of years instead of billions. A third option is that the first stars were more massive and shorter lived. They formed, fused elements, and exploded rapidly. Their deaths enriched the surrounding gas, triggering the next generation of star formation. This feedback loop could accelerate galaxy growth. Each explanation has problems. Efficient star formation should exhaust gas supplies quickly, limiting how large galaxies can grow. Denser dark matter halos should create different structure distributions than we observe. Rapid stellar turnover requires specific conditions that simulations struggle to reproduce. The simplest explanation is the most disturbing. Our models of galaxy formation are fundamentally broken. We do not understand how galaxies assemble. The processes we thought took billions of years can happen in a tenth of that time. The early universe was not a slow, gradual build-up of structure. It was an explosion of galactic formation happening far faster than physics should allow. These massive early galaxies also affect the universe's total mass budget. More galaxies mean more stars. More stars mean more heavy elements produced through fusion. The chemical evolution of the cosmos happens faster. Subsequent generations of stars and planets form from more enriched material. This reshapes our understanding of cosmic history. The timeline we taught in textbooks is wrong. Structure formation was rapid and violent, not gradual and orderly. The universe we thought we understood is stranger and more chaotic than we imagined. But the real shock comes when we examine how fast the universe itself is growing. Expansion is accelerating. For decades, cosmologists assumed the universe expanded at a steady rate or slowed down over time. Gravity should pull everything together. The Big Bang gave the initial outward push, but gravity should gradually break the expansion. The universe might expand forever, or it might eventually collapse back on itself. Either way, expansion should decelerate. In the late 1990s, two teams measured distant supernovae. Type Ia supernovae serve as standard candles. They explode with predictable brightness. By comparing their actual brightness to how bright they appear from Earth, astronomers calculate distance. By measuring their redshift, they determine how fast they are moving away. The teams expected to find that distant supernovae were closer than their redshift suggested. This would indicate the universe was expanding slower in the past. Instead, they found the opposite. Distant supernovae were farther away. The universe was expanding slower in the past than it is now. Expansion is speeding up. This discovery won the Nobel Prize. It also shattered cosmology. Nothing in known physics explains accelerating expansion. Gravity attracts. It does not repel. Some force must be pushing space apart, overpowering gravity. Scientists called it dark energy. Dark energy makes up roughly 68% of the universe's total energy content. It permeates all of space. It does not dilute as the universe expands. Regular matter spreads out, becoming less dense. Dark energy stays constant. As space grows, more dark energy appears. The expansion accelerates. We have no idea what dark energy is. It might be a property of space itself. Empty space could have intrinsic energy that drives expansion. This is called the cosmological constant. Einstein proposed it, then retracted it. It turns out he was right after all. Or dark energy might be a dynamic field. Its strength could change over time. Early in the universe, it was weak. Gravity dominated. Expansion slowed. Later, as matter spread out, dark energy became more influential. Expansion began accelerating. Or dark energy might not be a thing at all. Maybe gravity behaves differently on cosmic scales. General relativity works perfectly for stars, galaxies, and clusters. But at distances of billions of light years, gravity could weaken or change. Modified gravity theories attempt to explain accelerating expansion without invoking mysterious dark energy. None of these explanations are satisfying. They are patches. We invented a placeholder, dark energy, to match observations. We do not know what it is, why it exists, or how it works. It dominates the universe's energy budget, yet we understand nothing about it. Webb observations are making this worse. Precision measurements of distant galaxies allow astronomers to track expansion over cosmic history. The data suggest dark energy's strength might be changing. It could be getting stronger. If true, expansion will accelerate faster in the future. The universe will grow at an ever-increasing rate. This has implications for the universe's fate. If dark energy strengthens, expansion eventually becomes so fast that galaxies tear apart, then stars, then planets. Eventually, atoms themselves get ripped apart. This is called the Big Rip. It is trillions of years away, but it is one possible end for the cosmos. If dark energy weakens, expansion might slow down. Gravity could eventually halt it. The universe could collapse in a big crunch. Or expansion might continue forever at a diminishing rate, leading to a cold, dark heat death. We do not know which future awaits. We do not even understand the force determining the outcome. The universe's expansion is accelerating, driven by something that makes up most of its energy content, and we are clueless. The scale of our ignorance is terrifying. Does space end? Most people assume the universe has an edge, somewhere, a boundary where space stops. Beyond it, nothing. Not empty space, not darkness, literally nothing. No dimensions, no time. The concept breaks human intuition. Cosmologists consider three possibilities for the universe's shape. It could be flat, like an infinite plane. It could be curved positively, like the surface of a sphere. Or it could be curved negatively, like a saddle shape. Measurements of the cosmic microwave background suggest the universe is flat, or very close to it. Flat space extends infinitely. There is no boundary. Space continues forever in all directions. You could travel in a straight line for eternity and never reach an edge. This creates a paradox. If the universe is infinite now, it must have been infinite at the Big Bang. An infinite universe cannot expand into anything. It is already infinite. Expansion means distances between points grow. Galaxies move apart. But the total size remains infinite. This is difficult to visualize. Picture an infinite grid with dots spaced 1 unit apart. Now, double the spacing. The grid is still infinite, but the dots are farther apart. The universe expands the same way. Distances between galaxies increase, but the total extent remains infinite. If the universe is finite, it must curve back on itself, like a sphere's surface. Imagine living on the surface of a balloon. You could walk in any direction and eventually return to your starting point. Space is finite but has no edge. Travel far enough and you loop back. A finite, curved universe has measurable properties. Its curvature would affect how light travels. Distant galaxies would appear distorted in specific ways. The cosmic microwave background would show characteristic patterns. So far, measurements detect no curvature. If the universe is curved, the curvature is extremely subtle. A flat, infinite universe is philosophically unsettling. It means the universe has no center and no edge. Every point is equivalent to every other. Earth is not special. Our galaxy is not special. We occupy an arbitrary location in endless space. An infinite universe also implies infinite matter and energy. If space goes on forever and matter is distributed roughly evenly, there must be infinite galaxies, infinite stars, infinite planets. Somewhere, infinitely far away, another version of Earth exists. In fact, infinite versions exist. Every possible configuration of matter occurs somewhere if space is infinite. This is called the infinite universe hypothesis. It predicts that everything that can happen does happen infinitely many times. Every possible history plays out somewhere. The idea is mathematically sound but profoundly strange. If the universe is finite, the total amount of matter and energy is limited. The cosmos is a closed system. We could, in principle, count every galaxy and measure the total mass. The universe would have a definite size, even if we cannot see all of it. Determining which is true requires measuring the universe's curvature with extreme precision. Current data suggest flatness, but uncertainties remain. If future observations detect even tiny curvature, it would confirm a finite universe. If curvature stays zero, infinity is likely. Webb cannot answer this directly. It observes distant galaxies, but cannot measure global curvature alone. Combining Webb data with other experiments might narrow the possibilities. Patterns in galaxy distribution could reveal subtle curvature effects. The question of whether the universe is infinite or finite is not just academic. It determines whether existence itself is bounded or limitless. It affects the probability of life, the likelihood of other civilizations, the ultimate fate of the cosmos. And it makes the question of the universe's true scale even more terrifying. If infinite, the scale is literally beyond comprehension. If finite, we are trapped in a cosmic bubble with no way out. Either answer is disturbing. Cosmology is in crisis. For over a decade, scientists have known about a discrepancy in how fast the universe expands. The problem is not going away, it is getting worse. Precision improvements make the contradiction sharper. Multiple independent measurements confirm the mismatch. Something fundamental is broken. The Hubble constant describes expansion rate. It tells us how fast galaxies move apart per unit distance. Measure it accurately, and you know how quickly the universe grows. Calculate backwards, and you determine the universe's age and size. Two methods give different answers. The first uses the cosmic distance ladder. Start with nearby Cepheid variable stars. Their pulsation periods reveal their true brightness. Compare that to their apparent brightness from Earth, and you get distance. Use those distances to calibrate supernovae in distant galaxies. Supernovae provide distances to galaxies billions of light years away. From those, you derive the Hubble constant. This method gives 73 kilometers per second per megaparsec. It is precise. Multiple teams using different techniques agree. The error bars are small. The second method uses the cosmic microwave background. This ancient radiation emerged 380,000 years after the Big Bang. Tiny temperature variations in this light encode information about the early universe's density, composition, and expansion rate. Plug those measurements into cosmological models, and you predict how fast the universe should expand today. This method gives 67. The uncertainty is also small, 6 units apart. Both measurements are precise. Both have been checked exhaustively. Both should be correct. They cannot both be right. This is the Hubble tension. It suggests something fundamental is missing from our understanding. Either one measurement is systematically wrong in ways we have not identified, or the universe does not behave the way our models predict. If the cosmic microwave background measurement is wrong, our entire picture of the early universe is flawed. The standard cosmological model assumes the universe was hot, dense, and uniform early on. Tiny fluctuations grew into galaxies. Expansion has been smooth and predictable. If this model is wrong, everything built on it collapses. If the distance ladder measurement is wrong, we do not understand how to measure cosmic distances. Cepheids, supernovae, and other standard candles could be more complicated than we thought. Distances to galaxies could be incorrect. Maps of the universe would need revision. Or both measurements are correct, and something strange is happening. Dark energy might not be constant. It could vary over time or space. The universe might expand differently in different regions or eras. Physical constants, like gravity or the speed of light, could change. Some proposals suggest new physics. Maybe dark energy interacts with other forces. Maybe additional particles exist that affect expansion. Maybe the universe went through a phase transition that altered its properties. These ideas are speculative, but gaining attention as the tension persists. Webb was expected to resolve this. Its observations of Cepheids confirmed the 73 value. The tension did not disappear, it solidified. The crisis deepened. Cosmologists are genuinely worried. The field's foundational measurements do not agree. Textbooks might need rewriting. Theories might need replacement. Decades of work could be based on incorrect assumptions. The Hubble tension also affects the universe's size and age. If expansion is faster, the universe is younger and smaller. If slower, older and larger. We do not know which is correct. Our estimate of cosmic scale depends on resolving this contradiction. Some researchers propose abandoning the standard model entirely, build a new framework from scratch. Others insist the problem is systematic errors that better measurements will eliminate. The community is divided. What terrifies scientists is the possibility that the universe is genuinely stranger than our models allow. We built cosmology on assumptions: homogeneity, smooth expansion, predictable gravity. If any of those are wrong, we are not just refining details, we are fundamentally lost. The Hubble tension is not a minor discrepancy. It is a crack in the foundation of our cosmic understanding. And the things Webb is finding make the cracks spread. Light is fragile. Photons are massless particles carrying electromagnetic energy. They travel in straight lines through empty space at constant speed. They interact with matter by being absorbed, reflected, or scattered. Over cosmic distances, many things can happen to light before it reaches us. Webb detects photons emitted over 13 billion years ago. These particles began their journey when the universe was young. They traveled through expanding space for eons. They passed through clouds of gas. They skirted around galaxies. Gravity bent their paths. Expansion stretched their wavelengths. Yet they survived. The probability of any individual photon completing this journey is minuscule. Space is vast and mostly empty, but it contains enough matter to interfere. Intergalactic gas can absorb certain wavelengths. Dust grains scatter light. Even the thin hydrogen between galaxies affects photons passing through. For every billion photons emitted by a distant galaxy, only a handful reach Earth. Most are absorbed or deflected. The ones that make it are a tiny, biased sample. Webb's instruments must detect these rare survivors among overwhelming noise. The telescope's mirror collects photons. It focuses them onto detectors cooled to 7 degrees above absolute zero. At these temperatures, thermal noise is minimal. Sensors can detect individual photons arriving one by one. Over hours or days of exposure, enough photons accumulate to form an image. But these photons are not in their original form. Expansion redshifts them. A photon emitted as ultraviolet light 13 billion years ago arrives as infrared. The wavelength stretches by a factor of 10 or more. Webb's instruments are designed to detect these redshifted wavelengths. Hubble could not. Its sensors were optimized for visible and near-infrared. The most distant galaxies were invisible to it. Redshift also dims light. The farther a galaxy, the fainter it appears. Combine distance dimming with redshift, and distant galaxies are extraordinarily faint. A galaxy that would be bright if nearby becomes almost invisible when placed 13 billion light-years away. Webb overcomes this with time. Long exposures accumulate photons. The Hubble ultra-deep field exposed for 11 days. Webb's deep fields expose for similar durations. During that time, Earth orbits. The telescope must compensate for motion. Guiding systems keep it pointed at the same patch of sky to nanoradian precision. Each detected photon carries information. Its wavelength tells us what elements absorbed or emitted it. Its arrival time tells us about the source's variability. Its polarization reveals magnetic fields. By analyzing thousands of photons from a distant galaxy, astronomers reconstruct its properties. These photons also confirm the universe's expansion. If space were static, light from distant galaxies would arrive unredshifted. We would see ancient objects in their original colors. Instead, everything is redshifted. The farther away, the more extreme the redshift. This is direct evidence that space itself grows. Every photon Webb detects is a relic. It existed when the universe was a fraction of its current age. It witnessed cosmic history. It traveled through voids and clusters. It survived a journey that destroyed countless others. By the time it reaches us, it is stretched, dimmed, ancient, but it is real, and it brings information no other photon can provide. The farthest photons Webb detects come from near the cosmic horizon. They represent the earliest light we can see. Beyond them lies the Dark Age, a period before stars formed. Before that, the universe was opaque. Photons could not travel freely. They scattered constantly off electrons in hot plasma. The cosmic microwave background marks that transition. Before, the universe was opaque. After, it became transparent. Webb sees galaxies formed shortly after transparency began. It approaches the ultimate limit of observable time, but it cannot see everything. Some information is lost forever. There is a boundary we cannot cross. The cosmic horizon marks the farthest distance light can travel since the Big Bang. Beyond it, photons have not had time to reach us. Those regions are causally disconnected. Events there cannot affect us. Information from there cannot arrive. The horizon is an absolute barrier. As the universe expands, the horizon grows. More space becomes observable over time. Galaxies currently beyond the horizon will eventually cross into view as their light reaches us. But expansion complicates this. Accelerating expansion means some galaxies will never become visible. They recede faster than light can close the distance. Imagine a photon emitted from a galaxy far beyond the horizon. It travels toward us at light speed, but space between us and that galaxy expands. The expansion carries the galaxy away faster than the photon approaches. The photon makes progress, but the destination retreats quicker. It will never arrive. This creates a future horizon. Galaxies beyond it will never be observable, even if we wait forever. Expansion will carry them away faster than light can travel. They exist, but they are forever beyond our reach. Current estimates place the future horizon at roughly 16 billion light-years. Galaxies farther than that are moving away so fast that their light will never reach Earth. As dark energy drives accelerating expansion, this horizon becomes permanent. Objects within it remain observable. Objects beyond it disappear. What lies beyond the horizon? We do not know. Space could be similar to what we observe: galaxies, clusters, voids, all arranged in patterns resembling our observable region. Or it could be different. Maybe other regions have different properties. Maybe physical constants vary. Maybe the laws of physics themselves change. Some theories suggest the universe is a patchwork. Different regions, called domains, have different properties. We inhabit one domain. Beyond our horizon, other domains exist with different particle physics, different forces, different structures. The idea is speculative but mathematically consistent. Another possibility is the multiverse. Our observable universe could be one bubble in an infinite foam of universes. Each bubble has its own Big Bang, its own expansion history, its own physical laws. The space between bubbles is unreachable. We will never observe other universes, even in principle. These ideas are untestable with current technology. We cannot see beyond the horizon. We cannot send probes there. We cannot receive information from those regions. They might as well not exist for all practical purposes. But they do exist. The universe does not end at our horizon. Space continues. Matter exists there. Stars shine. Galaxies form. The cosmos extends beyond what we can ever observe. This is one of science's most humbling realizations. Most of reality is inaccessible to us. The horizon also affects our understanding of cosmic structure. We observe galaxy clusters, superclusters, and voids. These structures seem to form patterns, but we only see a limited volume. The patterns might look different if we could observe the whole universe. Our sample might not be representative. Imagine trying to understand Earth's geography by looking at a single square mile. You might conclude the world is mostly forest if that square mile happens to be wooded, or mostly ocean if it covers water. You would miss mountains, deserts, cities. The whole picture would elude you. We face the same problem with the universe. Our observable region might not represent the whole. The cosmos could be vastly more diverse than we can tell. Structures beyond the horizon could be completely different, or they could be similar. We cannot know. This uncertainty affects cosmological theories. Models assume the universe is homogeneous on large scales. What we see here should resemble what exists elsewhere. If this assumption is wrong, models fail. The universe could be wildly inhomogeneous beyond our horizon, and we would never know. The horizon also means most events in cosmic history are invisible to us. Galaxies form, collide, merge, and die beyond our view. Stars ignite and explode. Black holes devour matter. Civilizations might rise and fall. None of it reaches us. The majority of cosmic history happens unseen. We are trapped in a bubble. Everything outside is speculation. Records keep falling. When Hubble took its first deep field image in 1995, astronomers thought they were seeing the edge of the observable universe. Galaxies appeared at redshifts around 4. That corresponded to roughly 12 billion light-years. It seemed like the limit. Then deeper exposures found galaxies at redshift 5, then 6. Each new observation pushed the boundary further. By the time Hubble stopped making deep field surveys, it had detected galaxies at redshift 11. These objects formed less than 500 million years after the Big Bang. Webb changed everything within months. Its first deep field images revealed galaxies at redshift 12, 13, 14. Within a year, confirmed detections reached redshift 15. Some candidates might sit even farther. The record keeps breaking because Webb sees wavelengths. Hubble could not. High redshift means early times. A galaxy at redshift 14 emitted its light just 300 million years after the Big Bang. The universe was barely out of its dark age. Stars had just begun forming. Galaxies were assembling from the first generation of structure. Finding galaxies at these distances was not guaranteed. Models predicted they should exist, but predictions are not certainties. The early universe was chaotic. Conditions were extreme. Gravity, radiation, and expansion battled for dominance. Galaxies forming in that environment might be too faint or too small for even Webb to detect. Yet there they are, dozens of galaxies at redshift above 12, hundreds at redshift 10 or higher. They shine clearly in Webb's images. Many are bright enough for spectroscopy. Astronomers can analyze their light in detail, determining composition, star formation rates, and other properties. Each record-breaking detection raises questions. How did these galaxies form so quickly? Models say gas needs time to cool and collapse. Stars need time to ignite and evolve. Galaxies need time to merge and organize. Yet, here are structured, luminous galaxies when the cosmos was 200 or 300 million years old. The most distant confirmed galaxy sits at redshift 16.3. Its light was emitted 220 million years after the Big Bang. This is approaching the theoretical limit for galaxy formation. Before this time, the universe was too hot and dense for stars to form. After this time, structure formation proceeded rapidly. Finding galaxies this early suggests the transition from dark age to light happened faster than expected. Stars ignited sooner, galaxies assembled quicker. The first structures emerged within a few 100 million years of the Big Bang. But candidates exist at even higher redshifts. Some objects in Webb images might have redshifts above 20. If confirmed, they would represent galaxies forming just 150 million years after the Big Bang. This pushes into the realm of population. 3 stars, the theoretical first generation. Confirming these extreme candidates requires spectroscopy. Photometry, measuring brightness in different filters, gives rough redshift estimates. Spectroscopy splits light into wavelengths, revealing precise redshift through emission and absorption lines. Webb spectrographs are doing this work now. Each new spectrum might confirm or refute a candidate. Some high redshift candidates will turn out to be closer objects. Dust can mimic the color signatures of extreme redshift. Photometric errors can misidentify galaxies. Spectroscopy filters out false positives. The confirmed record might not reach redshift 20, but it will almost certainly surpass 16. Every new record shrinks the dark age. We thought this period lasted hundreds of millions of years. Webb is revealing it might have been much shorter. The universe transitioned from darkness to light rapidly. The first stars and galaxies emerged in a sudden burst, not a gradual build-up. This changes our understanding of cosmic dawn. The earliest stars were not scattered and isolated. They formed in groups, creating galaxies almost immediately. Structure formation was vigorous and efficient from the start. Each deep field Webb takes will likely break the previous record. The telescope has only begun its mission. More observations, longer exposures, and better analysis techniques will push the boundary further. We are witnessing the edge of observable time getting closer with each image. But even Webb has limits. Beyond a certain redshift, galaxies become too faint. Their light is redshifted into wavelengths Webb cannot detect. Even the longest exposures will miss them. We are approaching the absolute limit of what current technology allows. And when we reach that limit, we will face the terrifying reality of everything we still cannot see. Distance is not obvious in space. When you look at stars, they all appear equally far away. Some are brighter, some dimmer, but brightness does not directly tell you distance. A faint star could be intrinsically dim and nearby, or intrinsically bright and distant. Without additional information, you cannot distinguish. Astronomers use a cosmic distance ladder. Each rung relies on the one before. Start with nearby objects you can measure directly. Use those to calibrate more distant ones. Step by step, you build out to cosmological scales. The first rung is parallax. As Earth orbits, nearby stars shift position relative to distant background stars. Measure the shift, and you calculate distance through simple geometry. This works for stars within a few thousand light years. Beyond that, the shift becomes too small to measure accurately. The second rung uses standard candles. These are objects with known intrinsic brightness. Cepheid variable stars are one example. They pulsate at rates tied to their luminosity. Measure the pulsation period, and you know how bright the star truly is. Compare that to how bright it appears, and you get distance. Cepheids work out to tens of millions of light years. Beyond that, individual stars become too faint to observe. Even with powerful telescopes, you need a brighter standard candle. Type Ia supernovae fill that role. These explosions occur when white dwarf stars accrete matter from companions and reach a critical mass. They detonate in a runaway thermonuclear reaction. The explosion's brightness is remarkably consistent. Observe a type Ia supernova, measure its peak brightness and how it dims over time, and you know its distance. Supernovae are visible across billions of light years. They serve as the third rung of the ladder. By observing supernovae in distant galaxies, astronomers map the universe's expansion history. This is how dark energy was discovered. Beyond supernovae, you use galaxy properties. Certain types of galaxies have predictable relationships between their brightness, size, and rotation speed. Measure these properties, and you estimate distance. This works for galaxies billions of light years away. Finally, at the largest scales, you use redshift. For extremely distant galaxies, redshift becomes the primary distance indicator. Measure how much the light has been stretched by expansion, and you calculate distance. This requires assumptions about the universe's expansion history, which is where the Hubble constant enters. Each rung of the ladder introduces uncertainty. Errors accumulate as you climb. A small mistake at one rung propagates to all higher rungs. This is why the Hubble constant has been so difficult to pin down. Different paths up the ladder give slightly different values. Webb improves measurements at multiple rungs. Its infrared sensitivity allows it to observe cepheids in galaxies farther away than Hubble could reach. Better cepheid distances refine the supernova calibration. More accurate supernovae improve expansion rate measurements, but the ladder has gaps. Between nearby stars and distant galaxies, there are ranges where no single method works perfectly. Astronomers combine techniques, cross-checking results. Agreement between methods builds confidence. Disagreement, like the Hubble tension, signals problems. Measuring cosmic distances is also model dependent. Redshift to distance conversions assume a cosmological model, change the model's parameters, and distances change. If dark energy's strength varies over time, redshift-distance relationships shift. Galaxies that appear a certain distance under one model could be farther or closer under another. This creates circularity. We measure distances to determine cosmological parameters. We use cosmological parameters to measure distances. Breaking this loop requires independent checks. Observing multiple types of standard candles at the same distance helps. If they all agree, the model is probably correct. Webb's precision observations are tightening constraints. Better distance measurements reduce uncertainties in cosmological parameters. This should clarify the Hubble tension. If the measurements converge, great. If they diverge further, we know something fundamental is wrong. Distance measurement is the foundation of cosmology. Get it wrong, and everything built on it collapses. We trust our methods, but we are always aware of their limitations. We are measuring the universe with rulers calibrated by assumptions that might not hold. Every distance we quote comes with uncertainty. Even the most confident measurements have error bars, and those error bars affect everything we claim to know about cosmic scale. Time might be wrong. The Big Bang happened 13.8 billion years ago. This number comes from measuring the cosmic microwave background and tracing expansion backwards. Run the clock in reverse, and you find when everything was compressed into a single point, the calculation seems solid. But what if it is not? What if the universe is older? Finding massive, mature galaxies just a few 100 million years after the supposed Big Bang suggests a problem. These structures needed time to form. If the timeline is correct, they assembled impossibly fast. If the timeline is wrong, they had more time. An older universe solves some puzzles. Give galaxies an extra billion years, and their formation becomes less miraculous. Stars have more time to ignite, evolve, and explode. Supernova feedback has more time to shape galactic structure. The universe transitions from primordial gas to organized galaxies more gradually. How could the universe be older? The cosmic microwave background measurement could be wrong. Temperature fluctuations in that ancient light depend on the universe's properties when the light was emitted. If those properties were different than assumed, the derived age changes. For example, if the early universe expanded faster or slower than models predict, the time from Big Bang to microwave background emission changes. A faster early expansion means less time elapsed. A slower expansion means more time. Current models assume specific expansion rates based on matter and radiation content. Change those assumptions, and you change the age. Another possibility is that the Big Bang was not the absolute beginning. Maybe it was a transition or a bounce. Some cosmological models propose the universe existed before the Big Bang in a different state. It contracted to a minimum size, then expanded again. The Big Bang marks the bounce, not creation. If the Big Bang was a bounce, the universe could be far older than 13.8 billion years. The previous contraction phase could have lasted billions of additional years. Structures could have formed during that earlier phase, survived the bounce, and seeded rapid galaxy formation after expansion resumed. This is speculative. No direct evidence supports a bounce, but it is mathematically possible. Certain theories of quantum gravity predict bouncing cosmologies. The singularity at the Big Bang might not exist. Instead, quantum effects halt the collapse at extremely small but non-zero size. The universe bounces back into expansion. If the universe is older, distances are greater. Objects we thought were 13 billion light-years away could be farther. The observable universe could be larger than 92 billion light-years across. Everything scales up. An older universe also affects the timeline of structure formation. The first stars might have formed earlier than we thought. Galaxies could have assembled over longer periods, allowing more complexity and diversity. The cosmic timeline we teach might be compressed. Alternatively, the universe could be younger. If the expansion rate was higher in the past, the Big Bang could have occurred more recently. Everything would be closer and younger. This would make the early massive galaxies even more problematic. They would have less time to form, not more. Current evidence slightly favors an older universe. Webb's findings suggest galaxies formed earlier and faster than models allow. Extending the timeline eases the tension, but it creates new problems. An older universe requires different early expansion dynamics. Dark energy or dark matter properties might need adjustment. Testing whether the universe is older requires independent age measurements. The oldest stars in the Milky Way provide one check. Measure their ages through stellar evolution models, and you get a minimum age for the universe. If stars are older than 13.8 billion years, the Big Bang must have happened earlier. Some globular cluster stars appear to be close to that age limit. Their uncertainties overlap with the universe's age. This is uncomfortably tight. If future measurements find stars definitively older than the Big Bang age, cosmology faces a crisis. The age of the universe is not a trivial detail. It sets the scale for all cosmic history. Stars, galaxies, planets, life, all unfolded within that time frame. If the age is wrong, our entire narrative of cosmic evolution needs revision. Webb cannot directly measure the universe's age, but it can find objects that challenge the current timeline. Each impossibly early galaxy forces us to reconsider. Maybe the universe is older, maybe structure formation is faster, maybe both. Either way, something does not add up. The multiverse is not science fiction. Multiple universes, each with its own Big Bang and physical laws, could exist beyond our cosmic horizon. We cannot observe them, we cannot interact with them, but they might be real. One version of the multiverse comes from inflation theory. Inflation proposes that the early universe underwent a brief period of exponential expansion. Space doubled in size every fraction of a second. This expansion smoothed out irregularities and set initial conditions for the Big Bang. Inflation might not have ended everywhere simultaneously. In some regions, expansion stopped, creating a bubble universe like ours. In other regions, inflation continued, spawning more bubble universes. This process repeats endlessly. Inflation creates an infinite multiverse of disconnected bubble universes. Each bubble has its own Big Bang, its own expansion history, its own galaxies and stars. The space between bubbles continues inflating at enormous rates. The bubbles never collide or communicate. They are causally isolated. Our observable universe is one bubble. Other bubbles exist beyond our horizon, forever out of reach. They could have different physical constants. Gravity might be stronger or weaker. The speed of light might differ. Particle masses could vary. Each bubble is a separate experiment in physics. This raises the question of fine-tuning. Our universe's constants seem precisely calibrated for life. Gravity is strong enough to form stars, but weak enough to allow planets. The electromagnetic force is balanced correctly for chemistry. The strong nuclear force is tuned to allow element formation. Change any constant slightly, and life becomes impossible. Why are the constants so precisely set? In a single universe, it looks miraculous. In a multiverse, it is statistics. If infinite bubbles exist with different constants, some will randomly have life-friendly values. We necessarily exist in one of those bubbles. The others, empty and lifeless, go unobserved. This is the anthropic principle. We observe a universe compatible with observers, not because it was designed, but because we could not exist in one that was not compatible. Another multiverse version comes from quantum mechanics. Every quantum event creates branching realities. When a particle's wave function collapses, all possible outcomes occur in parallel universes. These universes are not spatially separated like inflation's bubbles. They exist in a different sense, as separate branches of reality. In the many worlds interpretation, every decision, every quantum measurement, every random event spawns new universes. The multiverse is constantly multiplying. Most branches are nearly identical to ours. Some diverge dramatically. This interpretation is mathematically equivalent to standard quantum mechanics. It makes the same predictions. The difference is philosophical. Do the other branches exist, or are they just mathematical artifacts? We cannot test this directly. A third multiverse version is mathematical. All possible mathematical structures exist as physical realities. Our universe is one such structure. Others, governed by different mathematics, exist elsewhere. This idea is even more speculative and harder to test. The multiverse is controversial. Critics argue it is not science because it makes no testable predictions. If other universes are unobservable, they cannot be confirmed or refuted. Proponents counter that multiverses emerge naturally from well-tested theories like inflation and quantum mechanics. Rejecting them requires rejecting those theories. The multiverse also has implications for cosmic scale. If it exists, the totality of reality is vastly larger than one universe. Not just billions of light years larger, infinitely larger, an infinite collection of infinite universes. This makes the question of the universe's size almost trivial. Our universe, even if infinite, is an infinitesimal fraction of the multiverse. Most of existence lies beyond not just our horizon, but beyond our entire cosmos. We might never know if other universes exist. But the possibility is not absurd. It follows logically from accepted theories. And it means the true scale of reality could be unimaginably larger than even Webb's deepest observations suggest. The universe we observe might be one bubble in an infinite foam. Everything we study, every galaxy Webb images, exists within a single, isolated pocket. The rest of existence stretches beyond, forever hidden. That is a terrifying thought. The timeline is breaking. Galaxies should not look old when the universe is young. Stars need time to form, fuse elements, and die. Supernovae need time to enrich gas with metals. Subsequent generations need time to incorporate those metals and build planets. The process takes billions of years. Webb found galaxies with mature features just a few 100 million years after the Big Bang. These are not clouds of gas with a few scattered stars. They are organized structures, spiral arms, central bulges, stellar populations spanning a range of ages. They look like modern galaxies, just redshifted into extreme distances. Spiral arms form through density waves. Stars orbit a galaxy's center. Gravity clumps them into trailing arms. This process requires stable rotation. Chaotic early galaxies should not have stable spirals. Yet, there they are, clearly visible in Webb images. Central bulges indicate past mergers. When two galaxies collide, their stars mix. Gas funnels toward the center, triggering intense star formation. The resulting bulge is dense and old. Building a bulge takes time. Multiple mergers over hundreds of millions of years are typical. Webb found galaxies with bulges at redshift 10. The universe was 500 million years old. These galaxies had already merged multiple times, formed stars in bursts, and settled into stable configurations. How? Stellar populations also reveal age. Young stars are hot and blue. Old stars are cool and red. A galaxy with both populations has been forming stars for a long time. Webb's spectroscopy detects these mixed populations in extremely distant galaxies. Some stars in these galaxies are already hundreds of millions of years old when the universe itself is barely older. This breaks the timeline. Stars cannot be as old as the universe. They need time to form after the Big Bang. Gas needs to cool. Dark matter halos need to collapse. Conditions need to stabilize. If stars formed immediately after the Big Bang, they would be as old as the cosmos. Webb's findings suggest some nearly are. One explanation is that star formation efficiency was higher early on. Gas converted into stars faster. Less material was wasted. More of the available gas ended up in stars. This would allow galaxies to build mass quickly. But higher efficiency creates problems. Rapid star formation exhausts gas supplies. Supernovae from massive stars blow remaining gas out of the galaxy. Star formation should shut down, not continue. Yet the galaxy's Webb seas are still actively forming stars. Another explanation is that dark matter halos formed earlier and grew faster. Denser halos provide stronger gravity. Gas collapses more quickly. Stars form sooner. This could explain why structure appeared early, but it requires revising dark matter models. Current simulations do not produce halos dense enough or early enough. A third option is that the first stars were different. Population. 3 stars, purely primordial, might have been extremely massive. They burned through their lives in a few million years. Their deaths enriched gas rapidly. Second-generation stars formed almost immediately. The transition from Pop 3 to Pop 2 happened fast. This compresses the timeline. Instead of taking hundreds of millions of years, early galaxy evolution happened in tens of millions. The universe bootstrapped structure formation quickly and violently. Each explanation has issues. Higher star formation efficiency lacks a physical mechanism. Denser dark matter halos conflict with observations. Rapid pop. 3 evolution requires specific conditions that models struggle to reproduce. The simplest conclusion is that we do not understand early galaxy formation. Our models, built on observations of nearby galaxies, do not apply to the early universe. Different physics governed that era. Conditions were too extreme for our assumptions to hold. This is humbling. We thought we understood how galaxies form. We traced the process from gas clouds to spirals and ellipticals. We built detailed simulations that matched observations. Then Webb looked farther back and found everything was wrong. The early universe did not follow our rules. It formed galaxies faster than we thought possible. It created structure when everything should have been chaos. It assembled complexity long before we predicted. Our timeline of cosmic evolution is broken. We need to rebuild it from scratch. And what Webb is revealing next makes things even more impossible. Existence requires time. A galaxy is not a simple object. It contains billions of stars, dark matter halos, gas clouds, dust, magnetic fields. All these components must assemble and organize. Gravity pulls matter together. Star formation ignites. Feedback shapes the structure. The process is gradual, or it should be. Webb found galaxies that assembled too quickly, not just slightly faster than expected, orders of magnitude faster. Galaxies that should take billions of years to form appeared in a few 100 million. The discrepancy is not a minor detail. It challenges fundamental physics. Consider what must happen for a galaxy to exist. First, dark matter collapses into a halo. This provides the gravitational well where normal matter accumulates. Early halos were small and grew through mergers. Simulations show this takes hundreds of millions of years minimum. Next, gas falls into the halo. It heats from compression. To form stars, it must cool. Cooling requires radiation. In the early universe, few cooling mechanisms existed. Hydrogen and helium radiate poorly. Cooling is slow. Gas lingers in hot halos before condensing. Once gas cools, stars begin forming. The first stars were massive and short-lived. They burned for a few million years, then exploded as supernovae. Their deaths enriched surrounding gas with heavier elements. These metals improved cooling efficiency. Second-generation stars formed more easily. Generations of stars live and die. Each enriches the gas. Each shapes the galaxy's structure. Supernovae drive galactic winds. Gas is expelled and later falls back. Star formation proceeds in bursts. Galaxies merge, mixing their stellar populations. Over time, organized structures emerge. This sequence takes billions of years in modern galaxies. Early galaxies should follow similar timescales, possibly longer due to inefficient cooling. Yet Webb found organized galaxies with mature features at redshifts above 10. The universe was 500 million years old. In that time, dark matter halos supposedly assembled. Gas cooled and collapsed. Stars formed, evolved, and died. Multiple generations succeeded one another. Galaxies merged. Structures organized, all within 500 million years. It is not just one or two anomalies. Dozens of these early galaxies exist in Webb's surveys. They are not rare outliers. They are common. The early universe was full of galaxies that should not exist yet. One possible explanation is that time itself behaved differently, not literally different clocks, but different physical processes. Maybe star formation proceeded faster. Maybe cooling was more efficient due to unknown mechanisms. Maybe dark matter collapsed more rapidly. Each of these requires new physics. Star formation efficiency depends on turbulence, magnetic fields, and feedback. Changing it means changing how gas behaves under gravity. Cooling efficiency depends on atomic physics and available radiation. Altering it means introducing new particles or forces. Dark matter collapse rates depend on its properties. Changing them means modifying the nature of dark matter itself. Another explanation is that our models are wrong. We extrapolate from nearby galaxies to the early universe. This assumes the same processes apply. Maybe they do not. Maybe the early cosmos operated under completely different rules. Extreme density, high radiation fields, unusual matter distributions. All could alter galaxy formation. If models are wrong, we must rebuild them. Observations of nearby galaxies would not apply to distant ones. The entire framework of galaxy evolution collapses. We would need new simulations, new theories, new assumptions. The most disturbing possibility is that time was not enough, and we are misinterpreting the observations. Maybe these early galaxies are not as mature as they appear. Maybe their light is tricking us. Dust, unusual stellar populations, or exotic physics could mimic signatures of age. Spectroscopy is revealing some of these details, but ambiguities remain. Each new Webb observation deepens the mystery. Every confirmed early galaxy adds to the evidence that something fundamental is missing. We thought we understood cosmic timescales, formation rates, evolution speeds. We were wrong. The universe assembled its structures far faster than our models allow. Whether through unknown physics, misunderstood processes, or completely wrong assumptions, the timeline we built is shattered, and it affects everything. If galaxies formed faster, so did stars. If stars formed faster, heavy elements appeared earlier. If metals appeared earlier, planets could form sooner. Life could arise earlier. The entire sequence of cosmic evolution shifts forward. We might be living in a universe where complexity emerged far earlier than we thought, where the conditions for life existed billions of years before we predicted, where civilizations could have risen and fallen long before Earth even formed. The scale of the cosmos is not just about size, it is about time. And Webb is showing us that time, like space, is far stranger than we assumed. Expansion is not movement. Galaxies do not fly through space like projectiles. space itself grows. The distance between objects increases because new space appears between them. This is fundamentally different from motion. Imagine ants on a stretching rubber sheet. As the sheet expands, ants move apart, but they are not walking. The surface under them is growing. Galaxies are the same. They sit in expanding space. They recede from each other without moving through space. This has strange consequences. Objects can recede faster than light. Light travels at 186,000 miles per second. Nothing can move through space faster than this, but space itself can expand faster. A galaxy embedded in that space recedes faster than light without violating relativity. Webb observes galaxies receding at multiple times light speed. Their light reaches us because photons travel through space, which is expanding. The photons make progress toward us even as the distance between us and the source grows. Eventually, if they are emitted close enough, they arrive. But there is a limit. If a galaxy recedes faster than a certain rate, its light will never reach us. The photons fight against expansion but lose ground. They travel toward us, but the destination retreats faster. These galaxies are beyond the cosmic horizon. Expansion also redshifts light. As space stretches, photons stretch with it. Wavelengths increase. Blue light becomes red. Ultraviolet becomes visible. Visible becomes infrared. The farther light travels through expanding space, the more redshifted it becomes. Webb detects light with redshifts above 15. This means wavelengths stretched by a factor of 16. A photon emitted as ultraviolet at 120 nanometers arrives as infrared at nearly 2000 nanometers. Webb's instruments cover this range. Hubble's did not. Redshift also dims objects. Not only does wavelength stretch, but photon arrival rate decreases. Imagine a distant galaxy emitting 1 photon per second toward Earth. As space expands, the time between photons arriving increases. Instead of 1 per second, we receive 1 every 2 seconds. The source appears dimmer. Combine this with distance dimming, and extremely distant galaxies are extraordinarily faint. A galaxy that would be bright if nearby becomes almost invisible when placed 13 billion light-years away and redshifted by a factor of 15. Expansion affects measurements. Distances depend on how much space has expanded during the light's journey. Calculate backwards from redshift and you get distance. But this assumes a cosmological model. Change the model's parameters and distances change. For example, if dark energy's strength varied over time, the expansion rate at different epochs would differ from current models. Galaxies at high redshift would be farther or closer than we calculate. The observable universe's size would change. Expansion also creates a horizon. Light from beyond a certain distance has not had time to reach us. This horizon grows as the universe ages, but acceleration complicates things. Objects currently beyond the horizon will eventually become visible as their light reaches us. But objects that cross the future horizon will never be seen, even if we wait forever. The expansion rate determines what fraction of the universe is observable. Faster expansion means a smaller observable region. Slower expansion means larger. Our measurements suggest roughly 10% of the total universe might be observable if the universe is finite, and much smaller if infinite. Expansion affects galaxy evolution too. Interactions between galaxies happen more frequently when space is denser. In the early universe, galaxies were closer together. Mergers were common. This drove rapid growth and triggered star formation. As expansion continues, galaxies spread out, interactions become rare, evolution slows. In the far future, expansion will isolate galaxies. Each will drift alone in an ever-expanding void. Stars will age and die. No new ones will form. Galaxies will fade. Eventually, isolated, dark, stellar remnants will be all that remains. Expansion guarantees cosmic loneliness. For now, expansion allows us to see distant galaxies. Their light, stretched and dimmed, carries information from billions of years ago. Webb captures this ancient light. Each photon is a relic from when space was smaller, denser, and younger. But expansion also hides the universe from us. Most of existence lies beyond our reach. We observe a growing bubble, but the totality of the cosmos expands faster. The fraction of reality we can see shrinks over time. We are racing against expansion. Webb pushes our observational boundary as far as technology allows. But the universe is pushing back, accelerating away. We see farther, but there is always more beyond. The universe is bigger than we can ever observe, and expansion ensures it always will be. Nothing outruns light. That is what physics teaches. Light speed is the universal limit. Matter, energy, information, all are bound by it. Accelerate a particle toward light speed, and its mass increases. Reach light speed, and mass becomes infinite. It cannot happen. Yet, distant galaxies move away from us faster than light, not because they are breaking physics, because space itself is expanding. Imagine a photon trying to cross an expanding universe. It travels at light speed through space, but space grows behind and ahead of it. The photon makes progress, but the destination recedes. If space expands fast enough, the destination moves away faster than the photon approaches. This is called recession velocity. It is not motion through space. It is the rate at which distance increases due to expansion. Recession velocity can exceed light speed without violating relativity. Relativity limits motion through space. It does not limit how fast space itself can grow. Space is not a thing that moves. It is the fabric in which motion happens. That fabric can stretch at any rate. Hubble's law describes this. The farther away a galaxy, the faster it recedes. Recession velocity equals the Hubble constant multiplied by distance. At large enough distances, this exceeds light speed. Current measurements place the Hubble constant around 70 kilometers per second per megaparsec. A megaparsec is 3.3 million light-years. A galaxy 1 megaparsec away recedes at 70 kilometers per second. A galaxy 10 megaparsecs away recedes at 700 kilometers per second. Extend this to billions of light-years, and recession velocities reach light speed and beyond. The crossover happens at roughly 14 billion light-years. Galaxies farther than this recede faster than light. We can still observe them if their light was emitted when they were closer. But light emitted now from those galaxies will never reach us. The photons fight a losing battle against expansion. This creates the cosmic event horizon. It sits at roughly 16 billion light-years. Galaxies beyond it are receding so fast that any light they emit now will never arrive. We are causally disconnected. Events there cannot affect us. Information cannot reach us. As dark energy drives accelerating expansion, this horizon becomes permanent. Galaxies currently observable will eventually cross it. Their light will redshift into invisibility. Future observers will see fewer galaxies than we do. The recession velocity of the most distant galaxies Webb observes exceeds 3 times light speed. Their light reaches us because it was emitted when the universe was younger and they were closer. Over billions of years, the photons crossed expanding space. By the time they arrived, the source had receded far beyond. This means we see galaxies where they were, not where they are. A galaxy at redshift 15 appears as it was 13 billion years ago. Today, that galaxy is roughly 46 billion light-years away due to expansion. It recedes at over 3 times light speed. If it still exists, it is unimaginably distant now. This disconnection between observation and current state is disorienting. Every image Webb captures shows the past. The farther we look, the more ancient the view. The present state of distant galaxies is unknowable. By the time their light reaches us, they could have merged, dispersed, or died entirely. Recession faster than light also means we can never visit those galaxies. Even traveling at light speed, we would lose ground against expansion. The destination recedes faster than we approach. No spacecraft could ever reach a galaxy beyond the event horizon. This limits the scope of future exploration. We might explore our local group of galaxies, the Milky Way, Andromeda, and nearby dwarfs. Beyond that, expansion wins. Distant galaxies are forever out of reach. The universe is filled with objects moving away from us faster than light. Most of existence is inaccessible. We observe a bubble, but the majority of the cosmos accelerates beyond our grasp. This is not science fiction. It is the reality of living in an expanding universe dominated by dark energy. Most of reality is unreachable. We are confined to a shrinking observable region. The universe is vast, and we are trapped. That realization is terrifying. How old is the universe? 13.8 billion years. That is the standard answer. It comes from measuring the cosmic microwave background and tracing expansion backwards. The calculation is precise. Uncertainty is less than 1%. Or is it? The Hubble tension suggests our measurements might be wrong. 2 independent methods give different expansion rates. If expansion is faster, the universe is younger. If slower, older. The discrepancy is small, but significant, a few 100 million years difference. That might not sound like much, but it matters. Stars, galaxies, and structures need time to form. Shave 1 billion years off the universe's age, and timelines get tighter. Add 1 billion years, and processes have more time. Webb's discoveries of massive galaxies in the early universe favor an older cosmos. These galaxies need time to assemble. If the universe is younger than we thought, they become even more impossible. If older, they are merely very difficult instead of absurd. Some researchers propose the universe could be as old as 15 billion years. This would ease tensions with early galaxy formation. Dark matter halos would have more time to grow. Stars would have more time to enrich gas. Structures could develop gradually instead of explosively. But an older universe creates new problems. The cosmic microwave background calculation would be wrong. The early expansion rate would differ from predictions. Dark matter or dark energy properties would need adjustment. The entire cosmological model requires revision. Alternatively, the universe could be younger. If the expansion rate is truly 73 instead of 67, the universe is about 13.2 billion years old. This tightens timelines even more. Early galaxies become more problematic. Stellar ages push uncomfortably close to the universe's age. Some of the oldest stars in the Milky Way are estimated at 12 to 13 billion years old. If the universe is only 13.2 billion years old, these stars formed within 1 billion years of the Big Bang. That is feasible, but requires very rapid early structure formation. The contradiction suggests one of several possibilities. First, one measurement method is systematically wrong. We have not identified the error, but it exists. Second, both methods are correct, and the universe is not uniform. Expansion rates vary by region or epoch. Third, our cosmological model is fundamentally flawed. If expansion varies, the concept of a single universe age becomes fuzzy. Different regions could have different histories. What we call the universe's age is actually the age of our local region. Other regions could be older or younger. This would shatter the cosmological principle. We assume the universe is homogeneous on large scales, the same everywhere. If expansion varies, this is false. The cosmos is patchy. Our observable bubble might not represent the whole. If the model is flawed, we need new physics. Dark energy might not be constant. Gravity might behave differently on cosmic scales. Unknown forces or particles could affect expansion. Decades of work could be built on incorrect foundations. Determining the true age requires resolving the Hubble tension. Webb is providing better data, more precise measurements of Cepheids, better distance estimates to supernovae, improved observations of early galaxies. Each data point refines constraints, but so far, the tension persists. Better data has not resolved it. The contradiction sharpens instead of fading. This is a bad sign. It suggests the problem is not measurement error, but something deeper. The age of the universe is not an abstract number. It determines cosmic history, the timeline of star formation, galaxy evolution, chemical enrichment, the emergence of life. If the age is wrong, everything built on it needs revision. We thought we knew when the universe began. Webb is making us question that certainty. Maybe the cosmos is older than we assumed, maybe younger. Maybe the question itself is more complicated than a single number can answer. Not knowing the universe's age is like not knowing what year it is. It is foundational information. Without it, we are lost. And that is exactly how the Hubble tension makes cosmologists feel lost. The universe grows in two ways. First, space itself expands. Distances between galaxies increase. The cosmos stretches. Second, the observable region expands. Light from farther objects has time to reach us. Our horizon pushes outward. These are not the same. Space expands faster than the observable region grows. Most of the universe races away from us faster than light can close the gap. The observable bubble increases, but it captures a shrinking fraction of the total. Right now, the observable universe is 92 billion light-years across. That is enormous, but it is smaller than yesterday. Not in absolute size, but as a fraction of the whole. Expansion inflates the total universe faster than our observable region grows. In 1 year, the observable radius increases by 1 light-year. Light emitted from objects, now at the edge, takes 1 year to reach us. As it travels, the edge moves farther due to expansion. The actual distance to the edge grows faster than 1 light-year per year, but we can observe 1 light-year deeper into space than we could before. This sounds slow. 1 light-year per year is nothing on cosmic scales, but given enough time, it adds up. In 1 billion years, the observable radius increases by 1 billion light-years. Galaxies currently beyond the horizon will become visible. However, dark energy complicates this. Accelerating expansion means some objects will never become observable, even given infinite time. They recede too fast. Their light fights expansion but never wins. The future cosmic horizon is permanent. Calculate the future horizon, and you get roughly 16 billion light-years. Anything beyond this distance is receding faster than light can ever overcome. We will never see it, no matter how long we wait. The observable universe has a maximum size. This maximum is larger than the current observable region. Right now, we see to about 46 billion light-years. In the future, we could potentially see to 16 billion light-years beyond that, but acceleration will prevent it. Objects approaching the horizon will redshift into invisibility before we can observe them clearly. The observable universe will effectively stop growing. Distant galaxies will fade from view. Their light will redshift beyond what any telescope can detect. We will see fewer objects over time, not more. In trillions of years, the observable universe will contain only our local group of galaxies. Everything else will have redshifted away. Future astronomers will see a lonely cosmos, a handful of nearby galaxies surrounded by darkness. They will have no evidence the universe was once filled with billions of galaxies. This creates a disturbing scenario. Future civilizations might conclude the universe is small and static. They would have no way to discover expansion, dark energy, or the Big Bang. The evidence will be gone, redshifted into oblivion. We are fortunate to live in an era where the universe reveals its history. Cosmic microwave background radiation still exists. Distant galaxies are still visible. Evidence of the Big Bang is abundant. In the far future, none of this will be accessible. The observable universe's growth is temporary. We are in a brief window where we can study cosmic history. Before this epoch, the universe was too hot and dense for stars or observers. After this epoch, expansion will erase evidence. We exist at the right time to understand the cosmos. But even now, we see only a fraction. The observable universe is tiny compared to the total. If the universe is infinite, we observe an infinitesimal portion. If finite, we might see 10% at best. Every year, our view expands by 1 light year. Every year, distant galaxies recede farther. The race between observation and expansion continues. We win locally, capturing more nearby space. We lose globally, as distant objects accelerate beyond reach. Webb pushes the boundary as far as current technology allows. Future telescopes might push farther, but there is a limit. The cosmic horizon is absolute. Beyond it, no telescope can see. No information can cross. The universe hides most of itself from us. We thought the cosmos was vast. It is vaster than we can ever know. Shape matters. We picture the universe as an infinite expanse, flat space extending forever in all directions. But this might be wrong. The cosmos could be curved, bounded, or topologically strange in ways our intuition cannot grasp. General relativity allows 3 basic geometries: flat space, like an infinite plane; positively curved space, like a sphere's surface; negatively curved space, like a saddle. Each has different properties. In flat space, parallel lines stay parallel forever. The angles in a triangle sum to 180 degrees. Space extends infinitely. This is what measurements currently suggest. In positively curved space, parallel lines eventually converge. Triangle angles sum to more than 180 degrees. Space curves back on itself. Travel far enough in one direction, and you return to your starting point. The universe is finite, but has no edge. In negatively curved space, parallel lines diverge. Triangle angles sum to less than 180 degrees. Space extends infinitely, but with a saddle-like curvature. This geometry is harder to visualize, but mathematically well defined. Measurements of the cosmic microwave background test curvature. Temperature fluctuations create patterns. Those patterns depend on geometry. Flat space produces specific correlations. Curved space produces different ones. Current data show the universe is flat to within 1% accuracy. If curvature exists, it is extremely subtle, but 1% uncertainty leaves room for surprises. The universe could be slightly curved in ways we have not detected yet. If positively curved, the universe is finite. You could, in principle, circumnavigate it. Light emitted from Earth might loop around and return from the opposite direction. We could observe our own galaxy as it was billions of years ago. This creates strange possibilities. Look far enough, and you might see the Milky Way repeated in multiple directions. Each image shows the galaxy at a different era. The observable universe could contain multiple copies of the same structure. Detecting this requires looking for repeating patterns in the distribution of galaxies. If the universe loops, distant galaxy clusters should resemble nearby ones. Statistical analysis might reveal correlations. So far, none have been found. Either the universe is not looped, or the loop is larger than the observable region. Topology adds more weirdness. Even in flat space, the universe could have strange connectivity. Imagine a three-dimensional version of a video game, where exiting one side of the screen makes you reappear on the opposite side. Space could wrap around in similar ways. A toroidal universe is one example. It is flat locally but finite globally. Travel far enough in any direction, and you return to your starting point. From the inside, it looks infinite. Only by mapping the entire structure would you realize it loops. Other exotic topologies exist. Mobius strips in 3 dimensions, Klein bottles, manifolds with handles and holes. Mathematics allows these, but physics might not. We have no evidence the universe has exotic topology. Curvature and topology affect the universe's size. A flat, infinite universe has no total size. A positively curved universe has a finite volume you could calculate. A toroidal universe has a specific size determined by where space loops. If the universe is curved or topologically strange, our distance estimates could be wrong. Light might take unexpected paths. Objects could appear in multiple places. The true scale of the cosmos might be very different from what we infer. Webb cannot measure global geometry directly. It observes local regions. But combining data from many sources might reveal curvature or topology, patterns in galaxy distribution, anomalies in the cosmic microwave background, repeated structures at different distances. None have been found yet. The universe appears flat and simply connected, but absence of evidence is not evidence of absence. We are probing with limited precision. Subtle effects could hide in the noise. The shape of the universe determines its fate. A flat universe expands forever. A positively curved universe might eventually collapse. A negatively curved universe expands forever, accelerating even without dark energy. Knowing the shape tells us the ending. Right now, we assume flat, but we are not certain. The cosmos could surprise us. Its true shape might be stranger than we imagine, and that would change everything. Webb has limits. Its mirror collects light. Its sensors detect photons. Its instruments analyze wavelengths, but there are boundaries. Faint objects disappear into noise. Distant galaxies redshift beyond detectable wavelengths. Even with perfect conditions, some things remain invisible. The faintest objects Webb can detect have apparent magnitudes around 32. Magnitude measures brightness. Higher numbers mean dimmer objects. The human eye sees down to magnitude 6. Hubble reached magnitude 31. Webb pushes slightly deeper. This might not sound like much. 1 magnitude is a small difference. But magnitude is logarithmic. Each step represents a factor of about 2.5 in brightness. Magnitude 32 is over 1 million times fainter than magnitude 20. At these limits, exposure time becomes critical. Faint galaxies require hours or days of observation. Photons arrive slowly, detectors accumulate them one by one. Background noise competes with the signal. Cosmic rays strike sensors, creating false signals. Patience and careful processing separate real objects from artifacts. Redshift creates another limit. Webb's instruments cover wavelengths from 0.6 to 28 microns. Light redshifted beyond this range is invisible. A galaxy emitting ultraviolet light at 100 nanometers and redshifted by a factor of 300 would appear at 30,000 nanometers. Webb cannot detect it. The highest observable redshift depends on the galaxy's original spectrum. If it emits strongly in the far ultraviolet, it can be detected at higher redshift. If it emits mostly in the visible, its redshift limit is lower. Current estimates suggest Webb can observe galaxies out to redshift 20 or slightly beyond. Beyond that, galaxies exist, but we cannot see them. Their light is too faint and too redshifted. Even longer exposures would not help. The photons simply do not arrive at wavelengths Webb detects. This defines the ultimate limit of Webb's reach. It sees to roughly 150 million years after the Big Bang. Before that, the universe was darker. Population, 3 stars might have begun forming earlier, but we cannot observe them directly. Their light is beyond our instrument's range. At the limit, galaxies are barely resolved. They appear as faint smudges. Determining their properties is difficult. Are they truly distant, or just intrinsically dim? Is the redshift correct, or is dust mimicking high redshift? Spectroscopy helps, but obtaining spectra of magnitude 32 objects is extremely challenging. Some objects at the detection limit might be false positives, noise fluctuations, cosmic rays, artifacts from image processing. Rigorous analysis filters these out. Only objects confirmed in multiple filters and exposures are considered real. The limit also depends on gravitational lensing. A galaxy too faint to detect normally might be magnified by a foreground cluster. Lensing can boost brightness by factors of 10 to 100. This brings otherwise invisible objects into view. Many of Webb's most distant galaxy candidates are lensed. Without magnification, they would be beyond detection. Lensing effectively extends Webb's reach. Instead of magnitude 32, lensed objects can be magnitude 34 or fainter before magnification. But lensing has limits too. Only objects aligned with foreground clusters benefit. Most of the sky has no strong lensing. Unlensed distant galaxies remain invisible. We see a biased sample, magnified by chance alignments. At the absolute detection limit, uncertainty dominates. Is that faint smudge a galaxy at redshift 20 or a closer object obscured by dust? Is the spectral feature real or noise? Did we truly find the most distant galaxy, or is it a statistical fluke? Confirming objects near the limit requires multiple independent observations, different instruments, different telescopes. If multiple teams using different methods agree, confidence increases. If results conflict, skepticism is warranted. Webb is pushing the boundary of what current technology can achieve. Future telescopes might go deeper, larger mirrors, better sensors, longer exposures. But there will always be a limit. Some galaxies will always be too faint, too distant, too redshifted. The universe extends beyond what any telescope can see. Webb shows us farther than ever before, but it also shows us how much remains hidden. The edge of detection is not the edge of reality. It is just the edge of our ability to observe. Science is supposed to clarify. You ask a question, you gather data, you analyze results, you find an answer. The mystery is solved. Understanding grows. Progress happens. Cosmology does not work that way. Every answer Webb provides generates new questions. Each discovery complicates the picture. We thought we were nearing complete understanding. Instead, we are drowning in mysteries. Example: Why do massive galaxies exist so early? Answer: star formation was more efficient in the early universe. New questions. Why was it more efficient? What physical process increased efficiency? Why does efficiency decrease over time? Did dark matter properties change? Were the first stars fundamentally different? How do we test these ideas? Each answer opens branches of inquiry. Webb's observations reveal phenomena we did not predict. Galaxies where they should not be. Redshifts beyond expectations. Structures too mature for their age. Every anomaly demands explanation. Explanations require new theories. New theories make predictions. Testing predictions requires more observations. More observations reveal more anomalies. The cycle never ends. This is normal in frontier science. When exploring the unknown, unexpected findings are common. Ptolemy's epicycles tried to explain planetary motion. Newton's gravity replaced them. Einstein's relativity replaced Newton. Each framework answered old questions but raised new ones. We might be at a similar transition. The standard cosmological model explains much: Big Bang, expansion, dark matter, dark energy, structure formation. It works well for nearby objects. But Webb is probing extremes: early times, distant objects, conditions the model was not tested against. Anomalies are appearing. The Hubble tension, early massive galaxies, rapid structure formation, unexpected galaxy properties. Each could be explained individually with ad hoc adjustments, but too many anomalies suggest systematic problems. Maybe the model needs replacement, a new framework that explains both old observations and new ones. This is how science progresses. Build a model, test it, find where it fails, build a better model. But cosmology faces a unique challenge. We cannot experiment. We cannot rerun the Big Bang. We cannot alter the universe to test hypotheses. We observe passively. We infer indirectly. We rely on models and assumptions. This makes progress slow. Each new puzzle requires careful observation, detailed analysis, and theoretical work. Competing explanations arise. Debates happen. Consensus is hard to reach. Webb accelerates this. It provides data faster than theories can keep up. Each deep field reveals dozens of puzzling objects. Each spectrum raises questions. The volume of mystery grows faster than the pace of understanding. This is exciting and terrifying. Exciting because we are discovering the universe is stranger than we thought. Terrifying because our models are breaking down. We thought we understood cosmic scale. Webb is proving we barely grasp it. Every answer creates 10 new questions. This is not failure. It is the nature of exploration. We are pushing into the unknown. The unknown pushes back. We learn the universe's true scale by discovering how much we do not know. Webb is not the end. It is the best telescope we have now. But better instruments are coming. Larger mirrors, more sensitive detectors, new technologies. Each will reveal more of the universe. Each will push the boundary farther. On the ground, extremely large telescopes are under construction. The extremely large telescope in Chile will have a mirror 39 meters across. That is over 60 feet. It will collect 17 times more light than any existing optical telescope. Ground-based telescopes face challenges. Earth's atmosphere distorts light. Turbulence blurs images. Adaptive optics compensate, but not perfectly. Water vapor absorbs infrared wavelengths. Observations require dry, high-altitude sites. Despite these limits, large ground telescopes provide advantages. Their size collects massive amounts of light. They enable spectroscopy of extremely faint objects. Combined with space telescopes like Webb, they offer complementary views. The giant Magellan telescope will have a 25-meter mirror. The 30-meter telescope, if built, will exceed that. Each will surpass current capabilities. They will observe fainter objects, resolve finer details, and probe deeper into cosmic history. In space, NASA is planning successors to Webb. The Habitable Worlds Observatory, proposed for the 2040 timeframe, would search for Earth-like planets. But it could also observe distant galaxies. A larger mirror and advanced instruments would extend reach beyond Webb's limits. Longer wavelengths are also critical. Webb covers up to 28 microns. Objects at very high redshift emit at longer wavelengths. A telescope covering 30 to 100 microns could detect galaxies Webb misses. This requires cooling to even lower temperatures and designs optimized for far infrared. Radio and millimeter telescopes contribute too. ALMA, the Atacama Large Millimeter Array, observes dust and molecules in distant galaxies. Future arrays with more antennas and better sensitivity will map the early universe in wavelengths invisible to optical telescopes. X-ray telescopes reveal hot gas and energetic processes. Future missions could detect the first black holes and supernovae. These events left signatures in X-rays that optical telescopes miss. Combining observations across wavelengths builds complete pictures. Optical shows stars, infrared shows dust, radio shows cold gas, X-ray shows violent events. Each wavelength reveals aspects others cannot. Future telescopes will also use improved analysis. Machine learning algorithms identify faint galaxies in noisy data. Better cosmological simulations predict what to look for. Statistical methods extract information from large surveys. Gravitational lensing will remain essential. Natural magnification from galaxy clusters boosts signals. Future surveys will map more lensing clusters. Targeted observations behind the strongest lenses will reveal the faintest objects. But even future telescopes have limits. There is a maximum distance determined by the cosmic horizon. No telescope can see beyond the edge of the observable universe. There is a minimum brightness determined by photon statistics. No amount of exposure can detect objects that emit too few photons. The ultimate limit might be the cosmic dark age. Before the first stars formed, the universe emitted no visible light. The cosmic microwave background marks the earliest direct observation possible. Before that, photons scattered constantly. The universe was opaque. Gravitational waves might probe earlier. These ripples in space-time travel unimpeded through matter. Primordial gravitational waves from the Big Bang could carry information from the first moments. Detectors like LISA, the Laser Interferometer Space Antenna, might observe them. Neutrinos also penetrate everything. A cosmic neutrino background exists, analogous to the microwave background. Detecting it would reveal conditions even earlier than the cosmic microwave background. Technology to do this does not exist yet, but future experiments might succeed. Each advance pushes us closer to the ultimate edge. We learn more about the universe's scale, its history, and its nature. But we also realize how much remains unknowable. The true universe likely extends far beyond anything we will ever observe. Webb shows us farther than humanity has ever seen. Future telescopes will go farther still, but the horizon will always recede. Most of reality will always lie beyond our reach. We are small, not metaphorically, literally, physically, insignificantly small compared to the cosmos. Earth is a tiny planet, orbiting an ordinary star in an unremarkable galaxy. Our local star is one of hundreds of billions in the Milky Way. The Milky Way is one of trillions of galaxies in the observable universe. The observable universe might be a minuscule fraction of the total. Scale that down to human terms. You are one of 8 billion people on Earth. Earth is one of trillions of planets in the galaxy. The galaxy is one of trillions in the observable cosmos. The observable cosmos might be one bubble in an infinite multiverse. The numbers are crushing. Your existence is a brief flicker in an incomprehensibly vast and ancient universe. Everything humanity has ever done occupies a point so small it barely registers. All our history, all our achievements, confined to one planet for a few thousand years out of 13.8 billion. Webb's discoveries amplify this. The universe is bigger than we thought, older in some respects, filled with more galaxies than we imagined. We keep finding more. Each observation shrinks our relative significance. This raises philosophical questions. If we are so small, do we matter? Does anything we do have meaning on cosmic scales? The universe does not care about humanity. It operated for billions of years before we existed. It will continue for trillions after we are gone. Some find this perspective liberating. Our problems are temporary. Our struggles, ultimately, irrelevant. The universe's vastness puts everything in perspective. Worries shrink. Petty concerns fade. Others find it terrifying. If nothing we do matters cosmically, why do anything? If the universe is indifferent, where do we find meaning? Existential dread sets in. We are alone, insignificant, temporary. But there is another view. We are the universe's way of knowing itself. Atoms forged in stars, assembled into complex structures. Those structures became living organisms. Organisms evolved brains. Brains developed consciousness. Consciousness created science. Through us, the universe observes its own scale. We build telescopes to see farther. We develop theories to understand deeper. We ask questions about existence itself. No other structure we know of does this. We might be rare, possibly unique. If intelligence is uncommon, our significance grows. We might be among the few, or only, beings asking these questions. The universe's vast scale does not diminish us. It amplifies the rarity of consciousness, but we do not know if we are rare. The universe is enormous. Even if intelligent life is improbable, sheer numbers might make it common. Trillions of galaxies, hundreds of billions of stars per galaxy, countless planets. Somewhere, other beings might wonder about their place too. Webb cannot answer this directly. It searches for biosignatures on exoplanets, oxygen, methane, water vapor. These could indicate life, but detecting intelligence requires different methods. Radio signals, megastructures, technological signatures. So far, nothing. The universe appears silent. Either we are alone, or we are not looking correctly, or civilizations are too far apart in space and time to communicate. The silence is unsettling. Discovering the universe's true scale also affects long-term thinking. Humanity's future, if we survive, spans billions of years. Our local star will burn for another 5 billion. If we colonize other stars, we could persist far longer. Trillions of years are available, but cosmic scale limits us. We can never explore the whole universe. Most galaxies will forever be beyond our reach. Expansion carries them away faster than we could ever travel. Our sphere of influence is bounded by physics. The observable universe defines our maximum domain. Anything beyond the cosmic horizon is permanently inaccessible. No matter how advanced we become, we cannot reach it. This sets an absolute limit on expansion. Accepting cosmic scale means accepting limitations. We are not central. We are not special. We are not infinite. We occupy a tiny region in space and time. Most of reality is closed to us. This humbles, but it also clarifies. Our actions matter locally. We shape our planet, our solar system, potentially our galaxy. Beyond that, the universe proceeds without us, and that is okay. Meaning does not come from cosmic significance. It comes from what we do in our limited sphere. The universe's vastness does not diminish our choices. It frees us to focus on what we can affect. Webb shows us the true scale of existence. It is overwhelming, but it is also beautiful. We are part of something unimaginably larger than ourselves. That is both humbling and awe-inspiring. We are small, and that is extraordinary. Some limits are absolute. No matter how advanced technology becomes, certain boundaries cannot be crossed. Physics imposes hard constraints. The cosmic horizon is one. The speed of light is another. These are not engineering challenges. They are fundamental. The cosmic horizon exists because light has finite speed and the universe has finite age. Photons from beyond a certain distance have not had time to reach us. This distance grows as the universe ages, but acceleration creates a future horizon. Beyond it, objects recede so fast their light never arrives. No telescope can see past this boundary. It is not a matter of sensitivity or mirror size. The information simply does not exist at our location. Events beyond the horizon are causally disconnected. They cannot affect us. We cannot affect them. This means most of the universe is permanently invisible. If the cosmos is infinite, the observable portion is infinitesimal. If finite, we see a limited fraction. Either way, most of reality is hidden. The cosmic microwave background creates another barrier. Before it was emitted, the universe was opaque. Photons scattered constantly off electrons in hot plasma. They could not travel freely. Observing earlier requires non-light methods. Gravitational waves, neutrinos, hypothetical particles. But even these have limits. The Big Bang itself might be opaque to all signals. Quantum effects at extreme density and temperature prevent information from escaping. The first moments of creation are fundamentally unobservable. If the multiverse exists, other universes are beyond our horizon. They are not just distant, they are causally isolated. No signal can cross from one bubble universe to another. We can never confirm or refute their existence through observation. Some theories propose fundamental limits to knowledge. The holographic principle suggests the universe's information content is finite. All information within a volume can be encoded on its boundary. There is a maximum amount we can know about any region of space. Quantum mechanics also imposes limits. The uncertainty principle prevents simultaneous precise measurement of certain properties. Position and momentum cannot both be known exactly. Energy and time have similar constraints. This is not a measurement problem. It is built into reality. These limits mean some questions might be unanswerable. Does the universe extend infinitely? We cannot observe infinitely far. Is time fundamental or emergent? We cannot probe below Planck scales. Are there other universes? We cannot access them. Science progresses by answering questions, but not all questions have answers. Some are beyond the realm of testable science. They become philosophy or speculation. This is uncomfortable. We want to know everything. We want complete understanding. But the universe might not permit it. Hard barriers exist. Beyond them, knowledge is impossible. Accepting limits is difficult. It feels like giving up. but it is realistic. We can push boundaries, we can extend our reach, but we cannot overcome physics. The horizon is real. The opacity of the early universe is real. The isolation of other universes, if they exist, is real. Webb pushes us to the edge of what is observable. Future telescopes will push farther, but eventually we will hit the wall. No amount of technology can break through. We will see as far as physics allows and no farther. The barrier is not a failure of science. It is a feature of reality. The universe has structure. That structure includes limits. We exist within those limits. Understanding them is itself a form of knowledge. We will never see everything. Most of the universe is hidden. The true scale of reality exceeds what we can ever observe. This is humbling. It is also clarifying. We focus on what we can study. We accept that some mysteries remain unsolved. The barrier reminds us we are finite beings in an infinite or near-infinite cosmos. We do our best with the tools available. We learn what we can. We acknowledge what we cannot. Webb revealed the universe is bigger than we thought. Future discoveries will reveal it is bigger still. But somewhere there is a limit, a final horizon beyond which we cannot see. That horizon defines the boundary of human knowledge. Everything beyond it is speculation. Everything within it is our domain. We cannot cross the barrier, but we can approach it. And in approaching, we learn just how vast, how ancient, and how terrifying the true scale of the universe really is.